This is the first video that I'm making to give a bit of an outline of the main ideas of Edmund Landau's book, The Foundations of Analysis, which was originally published in German some 90 or so years ago. I'm going to be referring to the English translation in these videos. I'll be sticking to the contents of the book quite closely for the most part, but I might from time to time raise some other issues, particularly things that may have come to my mind as I read the book, to draw attention to some things that I found particularly interesting or possibly requiring a bit more explanation. Also, from time to time, I'll spend a bit of time just taking stock of where we are and what some of the implications of certain theorems may be. I certainly don't intend to go through every single theorem in the book. There are some 301 theorems in total, so I just want to go through some of them to give a bit of an idea what is in the book and why it might be of interest for some people to read. This video is not meant to be a critique of the soundness of the approach or the soundness of the underlying mathematical philosophy used by Landau or anything like that. Whatever philosophy underlies the work is what we go along with in this video, and we accept it. So let's get a bit of background information on the book. The Foundations of Analysis gives a treatment of a possible development from the Peano axioms to the real numbers, and also to the complex numbers. The main development though is that leading up to the real numbers. Once the real numbers are done and dusted, then Landau goes on to the complex numbers, but these are really just an added bonus. The main show is the development of the reals, and that's what I'm going to be concentrating on in this video. Landau's book is just meant to show a possible way to get from the Peano axioms to the real numbers. It's not meant to, and nor does it deal with issues such as whether there are other possible axiomatizations or ways of constructing the reals, whether the axioms could lead to other number systems other than the reals, and there's very little in the way of philosophical investigation. Whatever the answers or lack thereof to these issues are not covered in this book. The work is it's got a very direct and clear purpose, and it sticks to that very closely. So despite being written almost a century ago, there's almost nothing that a modern reader with some familiarity with mathematical notation and ideas would find particularly unusual, controversial or offensive, and it all feels very familiar. Most people coming to this book will almost certainly have a good idea already, a good deal of familiarity with the natural numbers, reals, etc., and their properties. Through this book, you will learn practically no new properties of numbers that you didn't already know when you started. It isn't a book designed for that purpose. It really is just to show you how what you already know can possibly be deduced and proved from a certain initial set of axioms. So whether I recommend this book to someone depends entirely on what that person expects to get out of it, because it's very much for those types of people who like to see an axiomatic system doing its thing. The interest really comes from the development as a whole and not really from the individual theorems. The book will be a big disappointment for people who are expecting to learn interesting theorems or deep, exotic, number-theoretic properties of the natural or real number systems. The style of the book could probably best be described as minimalist, and this is one of the reasons that it could get very boring or disappointing for somebody expecting the wrong kind of thing from the book. Things typically fall into a few categories: axiom, theorem, definition, proof, and preliminary remark. And there's very little in the way of explanation or digressions. The theorems necessary to achieve the goal of constructing the reals are given. Any other implications that might come from those theorems and definitions that don't have any contribution to that ultimate goal are not really even considered. So you're expected to fend for yourself. There's no spoon feeding. The author rarely breaks things down to make them more understandable. If you don't understand it, then you have to sit and think about it until you figure it out. It's quite brutal in its approach. And this is evidently deliberately done to streamline the process as much as possible so that there's no redundancy in that development. Again, those who are into that kind of thing and accept the goal of the book will be the ones that are most likely, the ones that are going to get the most out of it. So Landau gives a bit of advice in the introduction, namely to forget what you've learned in school, you haven't learned it. He also says to please keep in mind everywhere the corresponding portions of your schoolwork, you haven't actually forgotten them. And although this is meant quite light-heartedly, it's worth bearing in mind the first point. Sometimes you really do have to work hard when you read this book to resist the temptation to impose your already existing knowledge of addition, multiplication, or the structure of these number systems onto these numbers before we've actually got round to proving these properties. So for example, the successor of a natural number is introduced in the axioms, but we can't take it as meaning from the outset the same thing as +1. For a start, addition isn't defined in the axioms, and nor is there initially an ordering on the natural numbers, so we can't assume that the successor of a natural number x is the next number along, or that it's greater than x. It's also interesting to note that Landau doesn't really expect his work to be taken too seriously. He says that it's written in such a way that a normal student can read it in 2 days. Probably took me a bit longer actually. And then since he already knows the formal rules from school, he may forget its contents with the exception of the axiom of induction and Dedekind's fundamental theorem. And there is some truth in what Landau says. After reading this book, I've forgot probably more than 95% of its contents within a couple of days because it's not really needed for anything. I can't remember the exact order of the theorems or the proofs off the top of my head, but I have a better understanding, a better grasp of how the development goes. And that's the important thing to take away from this book, having the satisfaction that you've seen the reals constructed from the Peano axioms, rather than just being constantly told that it can be done and taking somebody's word for it, but never having actually seen it for yourself. So let's get started, and the beginning seems like a good place to start. So even prior to stating the axioms that Landau develops the natural numbers and the real numbers from, there are some basic assumptions, some primitive notions maybe, that need to be introduced even before the axioms. So one of those primitive notions is that we assume the existence of a set or a totality of mathematical objects called the natural numbers. We've got to be very careful at this stage. Going back to what I was saying earlier in the video, that we've got to be careful not to impose our already existing knowledge about these things onto these numbers or these systems before we've actually got around to proving them. This is one such case because obviously there is some kind of underlying set theory here if we're assuming the existence of a set, but we don't know anything about how this set of natural numbers has come about. Is it something that is just assumed as an axiom within that set theory, or has this set of natural numbers been constructed from even more primitive notions within that set theory? We don't know. And on that note, we don't really know what is in this set of natural numbers at this particular stage. For all we know, this set of natural numbers could be the empty set. Obviously, we hope that that's not the case. We hope that there is actually something in that set for us to talk about. And when we get onto the axioms, that will definitely become the case. But for all we know, it could be the empty set. There might only be a finite number of objects in there. We can't assume anything about the structure of that set at this particular stage. So even though we really know what the natural numbers look like, we know what we're aiming for, we're not there yet. We're a long way from that point. Also, we assume a notion of equality between natural numbers that coincides really with what we'd expect from equality of natural numbers. So it's not, there's nothing unusual about it. Landau points out, although he doesn't use the term equivalence relation, he shows, it doesn't really even show actually, he just kind of states that it's got the right properties for it to be an equivalence relation. We've also got the notion of natural numbers not being equal to each other. So this is in contrast to equality. We've also got a notion of not equal to. And then we move on to the axioms. So altogether there are 5 axioms that we start with. I'm going to go through them one at a time, and I'm going to make a few comments on each of the axioms as I go through them. So the first axiom is, as written on the board, 1 is a natural number. So as innocuous as this seems, this is quite important because this axiom in and of itself guarantees at least that our set of natural numbers is not empty. We've got at least one natural number there, so at least we've got something to talk about. Again, obviously we kind of hope that there's going to be more natural numbers, but at least we've got something to talk about in there. In Landau's work, it's important to note that 1 is the only natural number that is ever explicitly referred to using the usual numeral notation for numbers. So occasionally 2 is referred to, but it's never referred to using the usual symbol for 2. It's referred to, once all relevant definitions and theorems and everything are in place, it's either referred to as, for example, the successor of 1 or 1 plus 1 or any other relevant notation, but it's never actually written as 2. So 1 is the only natural number that is explicitly referred to. So the second axiom is, for each x there exists exactly one natural number called the successor of x, which will be denoted by x prime. So this is effectively a function defined on the totality of the natural numbers, whatever that set looks like. So here we're assuming the existence of functions, which is quite an uncontroversial thing to do. And although intuitively, because of the language used here, the successor of x, we'd intuitively expect that to be x plus 1. But we can't say that at this stage because we don't have addition defined. We don't know anything about the structure of this particular function. And it doesn't actually mean that every natural number is a successor. It just means that every natural number has a successor. So there might be natural numbers that don't fall into the image of this particular function. It's also not meant to be taken as meaning that the successor is the next number along. Again, the language is used kind of preemptively, but at this stage we don't know that successor means the next natural number along. This successor function might have some very complicated behaviour. It might almost seem like a random assignment of one number to another natural, a pairing up of natural numbers. In time we will show that obviously that's not the case, that there is some definite structure to this that resembles what we expect it to resemble and justifying the use of the word successor, but we've got to get to that stage yet. Axiom number 3 states that we always have that x primed is not equal to 1. So what that means is that 1 is not the successor of any natural number. This itself doesn't mean that 1 is the only number that is not a successor. There might be other natural numbers that are not successors. In time, hopefully that possibility will be ruled out, but we've got to get there. But this actually guarantees that there is at least 2 natural numbers, because if 1 is not the successor of any natural number, then it can't be the successor of 1. So the successor of 1 must be a natural number by axiom 2, but it must be different to 1. So we've got at least 2 natural numbers. So it doesn't seem like much, but we are actually starting to gradually build up this structure and our knowledge of this set of what we call the natural numbers. Axiom 4 states that if the successor of 2 numbers x and y are equal, then in fact the numbers that we started with must have been equal as well. So if the successor of x equals the successor of y, then x is equal to y. So this prevents the successor function being a many to one function. So to get to a particular number, natural number, via the successor function, there's only one way that we can do that. So there's not different paths into a particular natural number via the successor function. So the 5th and final axiom is often referred to as the axiom of induction. Now this is an incredibly important axiom. Without this, a lot of the structure of the natural numbers as we know them to be wouldn't follow. So it simply says that let there be a given set M of natural numbers with the following properties, that 1, the natural number 1 belongs to M, and if x belongs to M, then so does x primed, its successor, then M contains all of the natural numbers. In comparison to the other axioms, this seems like quite a complicated axiom. There seems to be many more parts to this. It almost feels like that this ought to need its own proof, that this could actually be determined or derived from some even simpler principle. Whether that's the case, it's not of our concern here. We take this as an axiom because in a way this is seen really as capturing some of the essence really of what makes the natural numbers as we know them. And it's important to recognize that this system of axioms are specifically designed, specifically chosen because they capture in some way the behavior of the natural numbers as we expect them to be. So we're not interested in coming up with some system of axioms and just seeing where they end up. We already know where we want to end up. We're trying to capture some of that behavior, formalize it in some axioms, and that's where this axiom really comes from. So it doesn't require proof, with it, obviously with it being an axiom. Just some things to point out here. There is no notion of ordering here, so it feels like there ought to be. If we're starting at 1 and if x belongs to M, then so does the next. No, there isn't any such ordering. We actually don't know whether 1 is the first natural number. We just need that to be in the set. We don't know if x primed does actually follow x. We can't even talk about that at this stage because we don't have any notion of ordering. So as long as we've got a set that satisfies these requirements, even without a notion of order, we can make this conclusion that M contains all of the natural numbers. Again, it comes back to that idea of not imposing already existing knowledge onto these things at too early a stage. So they're the 5 axioms. On the question of whether these 5 axioms uniquely determine the natural numbers, well, okay, first of all, it's not really a concern to us in the study of this book. I believe that the answer to that is no, that there are systems of other mathematical objects that are structurally different to the natural numbers that satisfy these axioms, but such systems, such sets of objects, they're not our concern. We're specifically concerned with the natural numbers and eventually the real numbers. That's all we focus on in this book. So I'm going to move on now to the first few theorems. I'm going to go through the first 3 sections of Landau's book in quite a bit of detail. So these develop the structure of the natural numbers. So it's a question really of whether you see it as discovering or creating the structure of natural numbers, whatever your own personal philosophical persuasion is. But the first few theorems will certainly provide the evidence that we require in the form of theorems and proofs to show us that structure, that required structure is there, and that what we end up with is something that exactly resembles what we would recognize as being the natural numbers. So let's get started. So the first few theorems, maybe the first 36 theorems I think in Landau's book, cover addition, ordering and multiplication of the natural numbers. And as simple as these theorems and definitions seem to be, their importance really shouldn't be overlooked. Without these theorems, we wouldn't have the evidence that we require to show us that these axioms are actually determining the right kind of structure. So we've got an informal, intuitive understanding of what the natural numbers are. We need to make sure that these axioms are actually determining that kind of structure and not something else. So these are really important theorems. Some of them even though they're quite simple, they eliminate some really undesirable and pathological behaviours that we really wouldn't want the natural numbers to have. Sometimes it can be quite obvious which behaviours are being eliminated. Other times with some theorems it's not quite so clear exactly which behaviour is being eliminated. It might actually be that we need to use theorems in conjunction with each other to eliminate the possibility of certain undesirable behaviours in this set of natural numbers. So some of the theorems I'm going to go through in quite a bit of detail, so I might go through their proofs and give a bit of a commentary on the particular results. Other theorems I might write down but not really go into much detail with, and other theorems still I might actually just skim over. So particularly when it comes to the section on ordering, there's quite a lot of what would be kind of trivial theorems really. They're necessary but they're trivial. I'll talk a bit more about that when I get to that particular section, but I've tried to pick out the theorems that are that have the biggest contribution really to the development of the natural numbers. The first theorem is the following. That if x is not equal to y, then x primed is not equal to y prime. So it's a really simple, straightforward theorem. It's very similar to axiom 4 in a way. So axiom 4 states that if the successors of two numbers are equal, then actually the original numbers must have been equal. Well, this says that if we start at two different numbers and apply the successor function, we end up at two different places, so we can't end up at the same successor. So the proof of this, it's a simple contrapositive argument. At this stage, we've only got the axioms to work with. We don't have any other theorems, so the proof depends really on the axioms. So let's assume that x primed is equal to y primed, which is a typical start point for a contrapositive argument. Then so this is axiom 4. We get that x must be equal to y. Okay, so if the successors are equal to one another, then they must necessarily have come from two equal natural numbers, so, or a single natural number, if you prefer to think about it that way. So if the two numbers that we started with were different, we couldn't get to a point where we had two equal successors. So it's a simple theorem, but it just eliminates a certain amount of undesirable behaviour in our natural numbers. And this is what it is for these first few theorems and definitions. It's really chipping away at these undesirable behaviours, just gradually, bit by bit, until we get to something that's we can say that is what we recognise as the natural numbers. Okay, so moving on to theorem 2. So this simply says that x primed is not equal to x. So in other words, a natural number is never equal to its successor. This theorem is the first appearance, the proof of this theorem is the first appearance of the axiom of induction. So I'm going to go through this, the proof of this. What this theorem shows is that with the successor function there's no kind of stationary points, no fixed points. So the successor function is it's more dynamic in a certain sense, that if you apply the successor function you necessarily move to a different number. Not necessarily a new number, but a different number at least. You can't get to a certain point and just get stuck there, which is exactly what we'd want really with our natural numbers. So let's have a look. Let M be a set such that for every x in M, x primed is not equal to x. So M is defined to be the set of all the natural numbers for which this statement holds true. Well, obviously 1 primed is not equal to 1 because 1 cannot be the successor of any natural number, so this is axiom 3. So therefore 1 is in M. Assume x is in M. Then x primed does not equal x, because that's the definition of M. If x is in M, it's only in M if x primed is not equal to x. Then by theorem 1, we get that x primed is not equal to x primed. So just applying the successor function to each of these, we know that these two are not equal, then their successors cannot be equal by theorem 1. So therefore x primed is in M. So by axiom 5, or axiom of induction, M contains all natural numbers. Okay, so already this axiom of induction is really showing its power at giving us certain behaviours, determining certain behaviours that we find desirable, that we want our natural numbers to have. Without that axiom of induction, we wouldn't necessarily be able to show this. We might have a set that we're calling the natural numbers, but actually doesn't coincide at all with the kind of behaviour that we would expect from the natural numbers. So that's theorem 2. Now, this theorem as well, some of the kind of additional implications of this is it opens up the possibility now, the very real possibility of there being an infinite number of natural numbers. So actually up until now we didn't know whether we had a finite number, an infinite number of natural numbers. But now we can say that yes, actually we've got an infinite number, because if we start at 1, then we can get 1 primed. But 1 primed, it can't be equal to 1 by theorem 2, and also because 1 cannot be a successor of any number. So these two are not equal. So then we can move on to 1 primed. Well, again, this can't be equal to 1 because 1 can't be the successor of any number, and it can't be equal to 1 primed because that would contradict the theorem that we've just proved. Okay, so that means that this number is different to both of these. So, okay, let's move on to 1 primed. So we just keep applying the successor function. It can't be equal to 1 because then 1 would be a successor of a number, which we know it can't be by one of the axioms. I can't remember, axiom 3, sorry. It can't be equal to this by the theorem that we've just proved. How about this? Could it be equal to 1 primed? Well, actually no, because then that would mean that 1 primed is the successor of 2 different numbers, 1 and 1 primed. So we can keep playing this game, keep applying the successor function, and we can just get more and more different natural numbers. But it doesn't mean that that is the only kind of sequence of natural numbers. there might be other kind of start points. There might be other numbers that are not successors of any natural numbers. So we could start, let's say we've got x, which is not a successor of any number. We could do exactly the same thing. We might have finite loops of natural numbers. So we start with a number x, we apply the successor function, and we go around in a circle and we end up back at x at some point. So these are not ruled out at this stage. Gradually they will be ruled out, but we can't quite rule them out just at this stage. There might also be other much more complicated behaviours that we've not even considered. Okay. So theorem 3. So every x not equal to 1 is a successor. Okay, so this eliminates a definite undesirable behaviour. We know from our intuitive knowledge of what the natural numbers are that there are no numbers in there that can't be got at by addition of 1. Now obviously we haven't got to that stage yet formally, but we definitely want to rule out any possibility that we get behaviour that kind of contradicts that. So this does some of that work. It kind of eliminates the possibility of having a certain redundancy in our natural numbers, that we don't have these numbers that are not successors. So 1 is the only successor. So this theorem, just like theorem 2, relies on the axiom of induction for its proof. I'm not going to go through the proof, but again we can see the axiom of induction really coming into play to show us that it does give us these behaviours that we really want. Okay, so I'm going to move on to the next lot of theorems now.